One of algebra's many applications is to predict the behavior of variables. This can be done with exponential growth and exponential decay models for some sets of data. With exponential growth or decay, quantities grow or decay at a rate directly proportional to their size. This means that populations that are growing exponentially grow extremely rapidly as they get large because there are more adults to have offspring. Exponential growth and decay models are good at modeling populations that are growing or decaying rapidly over a short period of time. The mathematical model for exponential growth or decay is given by a equals a0 e to the kt power. Exponential growth is modeled when k is greater than 0, and exponential decay is modeled when k is less than 0. Example 1, in 1970, the U.S. population was 203.3 million and had grown to 308.7 million in 2010. So example 1a is to find an exponential growth function that models the data for 1970 through 2010. In the exponential growth model, a is the future amount, a0 is the starting amount, e is the mathematical number e, k is the growth rate, and t is the time. So what we're given in this problem is a future amount, a starting amount, and years, which will give us the time. So in order to come up with the exponential growth function, we need to know what the growth rate is. So filling in what we know the future amount is 308.7. The starting amount of our data is 203.3 million. E to the kt power. For times, I'm given a starting year of 1970 and an ending year of 2010. From 1970 to 2010 is 40 years. So our time is 40 years, and k is the growth rate that we need to solve for. In order to solve for k, this is an exponential equation, and we need to get the exponential alone. So first thing is to divide both sides by 203.3. Since that will lead us to a decimal, and we want to avoid as much rounding as possible, let's leave this as a fraction. So 308.7 over 203.3 equals e to the 40k power. Now that the exponential is alone, we can take the natural log of both sides. Remember that when we take the natural log of e, since the base of the log is the same as the exponential, this will simplify to just 40k. Our last step to get k alone is to divide both sides by 40. And so now k equals the natural log of 308.7 divided by 203.3 divided by 40. So if you type that into your calculator, just like I have written, natural log of 308.7 divided by 203.3, close parentheses, divided by 40, you'll get for an exponential growth rate 0.0105. And so your exponential growth function is a equals your starting amount, 203.3, e to the 0.0105 t power. So there's your solution to part A. Part B asks you to, according to the model, by what year will the population reach 335 million? So we're given a future amount and asked to find what year that will happen. So 335 million is our future amount, and that will equal 203.3 e to the 0.0105 t power. We'll solve this for t identically to how we just solved for k, by first dividing by 203.3 million, and then taking the natural log of both sides of the equation. The natural log of e will simplify and give us the natural log of 335 over 203.3 equals 0.0105t, and then finish solving by dividing by 0.0105. This same solving process will be repeated throughout this section. Okay, so typing this into our calculator, the natural log of 335 divided by 203.3, close parentheses, divided by 0.0105, gives us 47.57. So rounding to the nearest year, that's about 48 years. And to answer the question appropriately, it says in what year. So 48 years go by. Our starting year is 1970. Okay, so if you add 48 years to 1970, then that gives you a year of 2018. So in the year 2018, we would expect the population of the United States to be 335 million. Now let's talk about exponential decay. Radioactive decay is a common application for exponential decay. One such application involves using exponential decay in determining the age of fossils and artifacts. The method is based on considering the percentage of carbon-14 remaining in the fossil or artifact. Carbon-14 decays exponentially with a half-life of approximately 5,715 years. The half-life of a substance is the time required for half of a given sample to disintegrate. Thus, after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Carbon dating is useful for artifacts or fossils up to 80,000 years old. In example 2, let's use the half-life of 5,715 years to find the exponential decay model for carbon-14. So we know that the time will be 5,715 years. Okay, that's all the information we're given, but since we know that this is the half-life, that gives us more information that we can deduce ourselves. Okay, since after this amount of time, we'll have half of our original amount, it's irrelevant what our starting amount is. If I say the starting amount is 1, for instance, then the future amount is 1/2. If I were to pick 10 for my starting amount, my future amount would be 5. So the starting amount is irrelevant. The most convenient choice is the first one that I wrote down, 1 and 1/2. So if you're doing a half-life problem, use 1 for your starting amount and 1/2 for your future amount. Reason why this is most convenient is when we now solve for k, we'll have a future amount of 1/2 equaling our starting amount of 1 times e to the 5,715 k power. And we want to solve this for k. Well, since we chose 1, there's no dividing that needs to be done. I can right away go to taking the natural log of both sides. Okay, natural log of e simplifies away, leaving 5,715k. Dividing both sides of 5 by 5,715, we'll get k by itself. Okay, now on your calculator, if you are to enter this, let me show you what you'll see. We'll have the natural log of 1/2 divided by 5,715. And if you read your full screen, you have negative 1.21, bunch of numbers, and then e negative 4. If you don't remember what this means, this is calculator language for scientific notation. This means negative 1.21 times 10 to the negative 4 power. Remember, we convert scientific notation back to standard notation by moving the decimal place according to the power on the 10. Negative 4 tells me to move this decimal place 4 places to the left, which would require adding 3 zeros. So negative 0.000121 is our K value. The calculator uses scientific notation to show you more of the decimal number, cutting off the beginning zeros of your number. So our exponential decay function is A equals, we don't have a starting amount, that's irrelevant for a half-life problem, so A0 e to the negative 0.000121 t power. Part B says, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by a herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls in 1947. So we have a future amount of 76%. Our starting amount is not specifically stated, but if we're working with percents, your starting amount would be 100%, and as a decimal, 100% is 1. And then e to the negative 0.000121 t power. We wish to solve this for t. So exponential is alone already because we have a 1. So we'll proceed to taking the natural log of both sides. The natural log of e will simplify, leaving us with negative 0.000121 t. And our last step to solve for t, negative 0.00121 divided on both sides. So hopefully you've seen in the last 2 examples, we've gone through this exact same solving procedure now 4 times. You'll be using again this procedure over and over again in this section. So to get our t, natural log of 0.76 divided by negative 0.000121 on our calculator, and that gives us approximately 2,268. So in 1947, the Dead Sea Scrolls were approximately 2,268 years old. And to get the approximate age in this year, we would want to add on the difference between our current year and 1947. Okay, but to answer our question, in 1947, they were 2,268 years old, and now, of course, they are older than that.